Okay. We've talked about how we have our files and we can write code on those files and that code adheres to syntax of a programming language, and that programming language will have a compiler or interpreter that turns that code into an exe, which is machine code, which is which is given to a CPU and can be understood by a CPU, right? But let's talk about how the operating system comes into play in handling that, because an operating system plays a big role. It is the one who decides when does this exe gets run, right? Like you can choose to run it, right? But the operating system has final say. And how does the file system, how does how does the process of interacting with a file system get handled by the operating system when it is choosing to run exes, right? So let's go more in detail. Before we understand that, how does we have to understand that there's probably going to be a lot of there's not going to be just one exe running. It's going to be multiple, right? So we need to understand the sort of anatomy of one exe before we can understand everything else. Start off with our diagram we've seen before. It's the CPU, it's the RAM, and then this is a disk, or SSD. Okay, and then we have our exe. Okay, now whenever uh, whenever we're talking about a file in disk, it's called a program. Now we're talking about a file in RAM that the operating system is handling and thinking about, and it's called a process. So it goes from a program to a process, right? Okay. Now, those processes have what is called an address space. The address space is like all of the memory that the process is going to be able to think about. Say, this is my memory that I can use to store uh, heap heap information, static data code, etc. Right? So that that memory is called an address space, and then that address space, as you can see, is split up into multiple different types of memory encode. Okay, so you've probably seen stack, or sorry, you've probably seen heap. We talked about it. We talked about malloc, remember, or malloc, whichever, in the C++ section. You probably have not heard of stack. Stack is a data structure which is called LIFO. What does that mean? We have our variables here, and we have var1, var2, and then var2, var1 comes out, right? We want to remove from the stack, we do var2, var1. That's called a LIFO data structure whenever we have to reverse the order of our inputs and whenever we're outputting something, right? That's it. Okay. All fine and good. Nice, nice. Okay. So let's assume we have multiple EXEs in RAM. Okay. And we'll call them process 1 and process 2. Okay. So we have to we have to give both of them CPU time, right? So let's just go about thinking, okay, how do we do that? Well, the first thing we can probably do is say, okay, all right, you get or process 1 gets CPU for a bit, process 2 gets it for a bit, process 3, etc., right? You can think of it like this. Okay, now you're done. That next mm, next question. That is called a round robin structure, right? But here's the thing. What happens if P1 needs to request memory? It needs to request IO, right? Well, what happens is that this process, right, P1, is this is considered running. So the operating system considers it to be in the running state, right? It's running on the CPU. Well, then it needs to go to IO, and then it goes into the waiting state, right? Because it's waiting on IO, right? So it goes from running to waiting. Okay, so waiting, 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 and then it can go running again. And then we switch here. Let's say, for example, just for example, we're running. And then we have to get IO and we're waiting. Right? Then we switch, this one runs fine. But let's say that we're still waiting on IO whenever there's a switch again. And the CPU isn't doing anything here, right? And then it comes back and we can continue running. And let's say this is, at this point, if we run out of code, we're done. We can exit the process. And then that CPU handles this and says this is terminated. And then let's say let's move on and then blah, dot, 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 right? Okay. How do we handle that? Well, the CPU doesn't have any, or there's no CPU utilization over here. So what we can do is we can say, okay, go here, and then say this one goes fine and dandy, this one goes, and then we use the CPU here. This one goes, and then this one goes. So whenever there's a waiting for IO, we can interweave them together in order to make sure that we don't waste any CPU, right? That is called a scheduling algorithm. So whatever scheduling algorithm that we use is going to determine how processes are run on the computer, right? All right, fine and dandy. Okay. Next thing we have to handle. What happens, right? What happens when we say, okay, let's say I want to run 4 processes, right? P1, P2, P3, P4, right? Let's say these are all 3 gigabytes. These all require 3 gigabytes of RAM, right? Their address space is 3 gigabytes for each of them. Well, assuming this is 8 gigabytes, right? 8 gigabytes of RAM. We won't have enough space for all 4 of these, right? So how do we solve that if we want all 4 of these to be on there? Well, what we can do is we can say, okay, let's split up all of this, right, into what is called pages, right? So let's say each gets 50 pages, right? 50 pages for all of its stuff. All right, 50 pages. Now we have 50 pages. We can say, okay, 50 pages. And now it's all 50 pages. And we can say, okay, what are the 10 most used pages, right? 10 most used. And only those 10 most used get put into RAM, right? So we only use what we need to use in order to fight this, um, the fact that we don't have as much RAM as we need, right? Okay, all good and dandy. Okay, okay. So we have 50, so we use the 10 most relevant pages, and then we have that. Okay, here's the thing. Whenever, whenever we're talking about processes, right? They don't think in terms of, oh yeah, I'm sitting on the RAM, I should be accessing this instruction. Let's say this is DTA. Or let's make this a little bit bigger. Or actually, no, I can do something like this, where I say, okay, let's imagine this is an address space, right? This is data. Let's say at this location, right here, we're trying to access this location, right? Now, to the process, let's assume this is address 1, right? And then this is a representation of this data. Now, in the RAM, this is not going to be address 1, but to the process is only thinking in terms of itself. It's not thinking in terms of, okay, what is on the RAM? It's thinking, okay, what is this memory address relative to myself? So this is what is called a virtual address. And then say, okay, I want to access this virtual address. And what the CPU does is it uses a special component called the MMU. Okay, called the MMU to translate this address from the virtual address, which is just in the process's head. It's not really something we can do anything with, to something in RAM, which we can do stuff with. Okay, and that is called what is called virtual addressing, right?